Can you hear me? Can you hear me? No, you can't. Very well. Silence, please. You have to hear me. Because you're talking. Okay, so you shouldn't talk so that you can hear me. All right? Silence, please. All right. Let's start with a quiz question. So the quiz question is as follows. I'll give you 5 minutes or something, and then meanwhile we will collect all the signed papers of your quiz questions, and I will continue with the lecture, okay? I'll give you 5 minutes or something. So the question is as follows. This is a discrete time system which has the property that we have mentioned about in the previous hour, which is linear and time invariant. So this is a system which shows linearity property and time invariance property. And in short, it is linear and time invariant. And the input that we apply is an impulse, and the observed output is as follows. Some sort of a rectangular finite extent output from 0 to 2, all ones. This is the response. Remember that we gave a name to this, which is h of n. Now, the question is quite simple. If x of n is provided like this, a new input this time, 1, 2, and 3 are the values at 0, 1, and 2 over the n-axis. So this is our new input. What is the output? Okay, develop or obtain the output. This is a quiz question for the start, and all this week, throughout this week, we will learn how to do this anyway. So that's why I'm asking if you have any prior information, or if you can think of the solution of this. I'd like to see that. What, right, I want to know the output to this input. So let's give 5 minutes and give a break. So the reason of asking this question will be the method that we will see today, which will provide us to describe a system with respect to a particular input. First let me give you another example, a counter example to what I will show. Suppose that we make an experiment. For those of you who couldn't collect yet, that's fine. During the break you can submit anyway. Don't worry about that. So the experiment is as follows. We apply an input signal. Let's call this input signal as x1 of n. A discrete time signal as follows. At -1 it's equal to 1. At 0 it's equal to 2. And at 1 it's equal to 1. We choose this input signal to make a black box experiment, and we observe the output to an LTI system, linear and time invariant system. Output to this input is observed to be y1 of n, which is 1 and 1 at 0 and 1. This is an input-output relation that we observe at the end of this kind of input-output experiment. And then we want to determine the output to this new signal, which is x2 of n. We know that it's a linear and time invariant system. We don't want to repeat the experiment, so we just want to evaluate the output, which is like this. It is 2 at 0, 3 at 1, 0 at 2, and -1 at 3. This is our new input signal. And the question is, what is y2 of n? Now that we know that the system is linear and time invariant, it is given to be linear and time invariant, we would really like to decompose or express our new signal x2 of t in terms of the known signal here, which is x1 of n. So we want to express x2 of n in terms of x1 of n. Can you do that? Fortunately, for this particular case, you can do that. And x2 of n here is equal to twice x1 of n minus 1, which is this signal shifted towards right by 1 and scaled by 2. So it makes 2, 4, 2. Okay? Should I repeat what? I want to express x2 of n in terms of x1 of n. And while doing so, in terms of x1 of n will be a combination of x1, its shifted versions, and scaled versions, summing up. So 2x1 of n minus 1 will be one component, minus x1 of n minus 2 will be another component. What is that? x1 of n minus 1 is one shifted to the right of this thing, scaled by 2 because it's 2x1 of n minus 1. So it makes 2, 4, 2, right? Some signal like this, 2, 4, 2. This is 2x1 of n minus 1. What is x1 of n minus 2? It's that same signal shifted towards right twice. And there's a minus sign. It is scaled by minus 1. So it will be like this. Minus 1, minus 2, minus 1. So this portion corresponds to minus x1 and minus 2. And these are 2x1 and minus 1. And their combination is 2 here, the same. There's a 4 upwards and 1 downwards. There's a 4 minus 1, which makes 3. This is 2 plus and then minus 2, which makes 0. And a minus 1, which makes a minus 1. So that's what it is in terms of the input. And we know that from linearity and time invariance, the output to this component is just shifted output to this component towards right by 1 and scaled by 2. We scale the input by 2, the output is also scaled by 2. It's linearity. And the input is shifted, the output is also shifted. So what I claim is, to this particular portion, the output is 2y1 n minus 1. And to this particular input, the output is minus y1 n minus 2. And since I combine the inputs, the outputs are also combined to obtain y2 of n. And what does it make? Let's use some colors, but we don't have many colors. So anyway, y1 of n was this 1, 1. y1 of n minus 1 is one shifted towards right. It starts from here, and it is scaled by 2, so it is 2 and 2 at 1 and 2, and minus y1 n minus 2. y1 n is this one, y1 n minus 2 is 2 shifted towards right. So it starts from 2. I'll draw with a yellow, but I don't know whether it's visible. And it's scaled by minus 1, so it is minus 1 and minus 1. This is this portion. These two positive samples is this portion. And their combination is, it will be a 2 at 1. It will be 2 minus 1, which is 1 at 2, and minus 1 at 3. So this is y2 of n, graphically. But we were too lucky to solve this question, to solve this kind of a question. It's not always possible that x2 of n could be achieved in terms of this x1 of n. The example was deliberately chosen that way. The design of this question was such that I could obtain x2 of n in terms of x1 of n using that equation. But it's not always possible. It's not in general true. We cannot do that. If the signals, the x1 signals are designed this way. However, it's always possible to have one x1 of n signal such that you can always define or design your new signal in terms of that particular signal. And what is that particular signal? What is the best choice for x1 of n? If you were to do an experiment, you should always choose an impulse, a unit sample, and see its output, which is the impulse response for LTI systems. Because we know that every signal can be expressed in terms of impulses. There's an expression to do that. I'll erase this portion and continue from there. I'm going to keep this quiz question here because we will solve it anyway, eventually. Okay, so the good experiment is as follows. We input an impulse, a unit sample, to the LTI system, and we observe the output, and we call it h of n, which is the impulse response. That's a particular name. And I'm claiming that we can always describe any kind of other signals, x of n, and I can find the output y of n for this case. And how do I do that? Let's first try to express x of n in terms of impulses. We did that before. Last week we already covered this. What is x of n? For instance, all right, let's come back to here. Let's continue with this example. What is x of n in terms of impulses? That's one impulse I can see here. This is unit sample. Plus 2 times, that's a delta, by the way, the name. N minus 1. Because it's shifted once to the right. And then we have 3 times delta n minus 2. Now, a nice property about this is, although it's implicit, we know that the values are 1, 2, and 3. Let me write it like this. What is 1? That is x of 0. In general, whatever the value here we have, our signal would be x of 0 times delta n. It could be 1, it could be any other value, it could be pi, it could be 7.1. Plus, what is this value, x2? It's the value of x at n is equal to 2, or k is equal to 2. 1. K is equal to 1. So I'm going to write it like this, x of 1 delta n minus 1. And 3 is, coincidentally, x of 2 plus x of 2 delta n minus 2. And it goes on like this. x0 delta n minus 0 plus x1 delta n minus 1 plus x2 delta n minus 2. the support of this signal is from 0 to 2, so this much is fine. But in general, for any arbitrary x of n, can you give me the formulation of this summation? It's a summation, so let's write it like a summation. It can be tab 3, length 3, but it can be more. It can be from minus infinity to infinity. It can be infinitely long. It's just an input. So what is it? K from minus infinity to infinity. Not even from 0. It could also go to the left. So it's from minus infinity to infinity. What do we have? Yeah. All those running indices must be inside x. X of k delta n minus k. So what we observe here is that any kind of an x of n can be written in terms of shifted and scaled impulses. And here the scales are x of k's, and they are numbers. They are the values of this x function, discrete time x function. They are values. These are not signals, okay? Be careful about that. I've mentioned about this last week, but I have to insist because this is one of the most confusing things for the students. Usually you interpret this x of k as a function, but you see that the running index is k. So for every k inside this running index, x of k is a value. For example, x of 1. And what is that? What is x of 1? It is 2. So it is this value that I'm talking about when I say x of 1. It's the value. These are scales, and these are shifted impulses. Linear combination of shifted and scaled impulses. And we know that for the first impulse in the center, it's not the first impulse, it's one impulse in the center, we know that the output is h of n. All right? So if you shift the impulse response will also be shifted. So to delta n, the system output is h of n. To delta n minus 1, the system response is h of n minus 1. Why? Because it is time invariant. The system is given as time invariant. If the system is not time invariant, you cannot assume this, of course. Delta n minus 2 produces h of n minus 2. And it goes on like this. And then this x of n is multiplied by 1 for this quiz question example. So the output is 1 times h of n. Then in the input we have 2 delta n minus 1. So the input is not delta n minus 1, but it is 2 delta n minus 1. Then what can we say about the output? 2 h of n minus 1. Working the same way. Why is that? Why is the input scaling the same as the output? Yeah, that's the linear system which is also given. And 3 times delta n minus 2 will produce 3 times h of n minus 2. And we say that the input is the summation of these things. So what is the output? The output is the summation of these individual outputs then. You must add them up. So compare your results with this output then. H of n is this. H of n minus 1 is 1 shifted towards right and scaled by 2, so it is 2, 2, 2 like this. And finally, h of n minus 2 is starting from 2, and its value is 3. So it is 3, 3, and 3. And we must add up these 3 components. What is that? How can we plot in the end? At 0 we have 1. At 1, we have 1 here, and 2 here, and nothing here. So it is 1 plus 2, which is 3. Then at 2, we have 1, we have 2, and we have 3, which makes 6. The scale is a little bit bad, sorry about that. And then at 3, we have nothing from here, but we have 2 and 3 from here, so it makes a 5. And at 4, we have only 1, 3 here. And after that, we have nothing. Before that, we have nothing. Like this. So this is the expected result from your quiz. This is y of n. That's good. So now, let's alter these input-output relations. Instead of 1, 2, and 3, which are some certain numbers, let's give more generic values to those things. It's not even values that I'm talking about. It is x0, delta n will produce x0 h of n. And here we have x1, delta n minus 1, and the output is the same x1 times h of n minus 1, because x1 is a scale which amplifies or attenuates delta n minus 1. This is a scale. The same scale is scaling h of n minus 1. X of 2 times delta n minus 2 will produce x of 2 times h of n minus 2. And we are just adding these up, and it was summation from minus infinity to infinity xk delta n minus k will produce the same summation as the same summation, right? K from minus infinity to infinity, the same scales, x of k, and every impulse will produce the corresponding h. Delta n minus k will produce h of n minus k. And I'll give a name to this. It is y of n. Y of n is equal to this. This is an expression that you will commonly encounter, and you will have to use it. And it has a name. Do you know the name already? Some of you guys are maybe taking this course twice or 3 times already. So any idea about the name of this equation? Convolution. We are convolving the x and h. And this formula describes the essence of this linear and time invariant systems. If you know the impulse response h, then you can always use this formula to find the output y to any input x. So what you really need to do is, of course, you need to know the input, otherwise you cannot determine the output anyway. So you know x, it must be given to you. You must also determine experimentally, or I must give you in the question, the impulse response h. These must be given to you. Look at the quiz question once again. I said that the impulse response is this. So I have given you this. And I also gave you the input. Therefore, what you really need to do is you have to convolve the input and the impulse response using that formula. There is even a nice notation for the operator of convolution. that is a single star. Maybe I should write it over there. Well, but there is more space here. Sorry, excuse me. So let me use this box. Y of n is equal to the convolution of x of n and h of n. And you use a star in between. That is the notation for convolution. And that is equal to summation from minus infinity to infinity xk h of n minus k. This is our famous linear and time invariant system response formula, also known as I say, convolution. Okay, you have to remember this. If you have difficulty in remembering things like I do, I'm very bad at remembering things. Every time I need to find an output, I forget about the convolution formula. What was that? I say to myself. But as you see, throughout describing you this convolution sum, this is convolution sum which is valid for discrete time signals because it's in the form of a summation. In the continuous case, it's a bit more complicated than this one because it's a convolution integral it will become. But let's come back. If you are bad at remembering things like I am, then I have to design the output formalism all over again. As I said, I didn't use any papers or anything to make that derivation because I know how to derive it. Believe it or not, when you ask me the convolution sum, what is the convolution sum? Well, I will be able to write down the convolution sum. I will be able to remember after so many years. But every time, I first think of the representation of x in terms of impulses. This is easier for me to remember. I don't have to memorize anything for this. From here, I replace these deltas, impulses, with the impulse responses, and automatically what I obtain will be the convolution sum. That's how I always remember convolution. Of course, every student will have his or her own way of interpreting things. That's how I understand this thing. If you are familiar with memorizing things, then you may just memorize this convolution. It will be very convenient for you. This is the convolution. And convolution has many nice properties for solving questions or determining the outputs of linear and time invariant systems to particular inputs. And what could they be? Okay, the first property that we can mention is the commutation property or the commutative property of convolution. What I mean is this. I said that y of n is equal to x of n convolution with h of n. This convolution is a linear operator because it is describing a linear and time invariant system. Linearity is inside it. What is an example of a linear operator that you can think of? It could be a summation, for example, or a multiplication. What I'm saying is that you can interchange the convolving parameters. You can change the orders of them. So y of n is also equal to h of n convolution x of n. That's a strange property, and it is quite useful in several cases. Let's verify it. Let's verify it over an example here. The same example that I didn't erase. And let's see if the opposite of h and x holds. So what I'm saying is this. suppose that this h of n is not the impulse response, but let's assume that it's our input. To a system with an impulse response like this, so let's call this thing to be the impulse response now. Previously I said this is the input and this was the impulse response. Now I'm replacing the orders. And let's try to solve the same question. If the input is this, how can I find the output? Let me first find the output to this impulse. So it's 1, 2, and 3 to this impulse. Let's find the output to the next impulse, one shifted towards right. How do you find the response? It is the same output shifted towards right, okay? Because the new impulse is one shifted towards right. And to this impulse, the output will be 2 shifted this time. And remember that all these values are 1, so I'm not scaling anything. I'm just shifting towards right. Right? These are the individual responses, and what you really need to do is you just need to collect them, add them up. What will you obtain? You will obtain 1 at 0 and 2 plus 1, which is 3 at 1, and 3 plus 2 plus 1 at 2, which is 6. Then 3 plus 2 at 3, which is 5. And then only this 3 at 4. Is it the same as the previous result? It must be. So we have verified this property, but that's just a verification. I didn't prove or anything. That would be a very nice idea to try to prove it, but it's something like so fundamental that it may be difficult to prove. To prove that when you replace the orders of x of n and h of n like this, you will get the same thing. Now let's see another example which is a little bit more involved, because this example will not be finite extent. It will be a bit complicated. Suppose the impulse response of a discrete time linear and time invariant system is given as h of n equals u of n. Now what is that? The impulse response is a unit step function. When you apply an impulse, the output jumps to that value and it stays at that value. From that, determine the output to this input, alpha to the n u of n. As if this one is not enough, I'm giving you an input which is also infinite extent. Here, alpha is less than 1 in magnitude, so that it's a decaying exponential. Then, how can we determine the output, or can we write a compact form of this expression? Alpha to the n u of n. What is that? First, try to visualize this x of n. It's a 1 at 0, because alpha to the 0 is 1. Notice that whenever you see times u of n in any signal expression, you must immediately understand that that signal starts from 0 and goes to the right. U of n multiplication by a u of n prohibits these negative values immediately. That's a very convenient way of writing signals that are right-hand sided only, for example. So you could also say that x of n is equal to an alternative expression. It's equal to alpha to the n for n greater than or equal to 0, and it is 0 else. Okay, writing this thing in a more compact way is alpha to the n u of n, writing it like that. And we usually use it that way. So at 0, starting from 0 and onwards, we have the signals. At 0, it is alpha to the 0, which is 1. At 1, it is alpha to the 1, which is alpha, which is less than 1. And it's a decaying exponential, as you may guess. Then you have alpha square at 2, then alpha cube value at 3, alpha to the 4 at 4, alpha to the 5 at 5, etc. It goes on like this. These are the values that you have. Okay? And for each value, for each impulse, we generate some amount of outputs. You have to pay attention to what I'm saying and writing. So try not to take notes for this thing because it will be a little bit complicated. It will be complicated even here. And I'm sorry about that. But what I'm saying is this. To this impulse, in the center, we have the impulse response to be let's put a 1 here. Okay, let's say that 1 is here. Sorry that these two 1s are not measuring the same values, but this will be collected and growing anyway. That's why I started with a smaller one. All right? And it will be a unit step function. So it is all 1s like this. And it goes on. This is the response to the first. Then what comes? Then comes this new impulse whose size is alpha. Its size is not 1, and it is 1 shifted towards right. Therefore, the response is also a unit step function which is starting from 1, not starting from 0, shifted towards right. And its value is alpha. It's not 1. Let me use this yellow chalk. I'm trying to draw an incremental bar on top of these whites, and the size of this incremental bar is alpha, and it's all alphas that are added on top of this. Okay, then let me have a different color. Let's try with the green. This alpha square is the new impulse. It starts from 2 and it generates a unit step function starting from 2 whose size is alpha square. It's not alpha or 1. It is smaller than alpha. So let's assume that it's this green bar. Oh, sorry, it's not there. It's here. This green bar is alpha square tall, and it is added starting from here. And it goes on. And the next example is similarly, this time alpha cube. It is even shorter with a purple chalk. This increment is alpha cube. Then will be alpha to the 4, then alpha to the 5, then alpha to the 6, then alpha to the 7, etc. As you see, as you go along here, more and more alpha to the power terms will be added on top of it. And this is also an exponential curve which has a limit value. What is that limit at the end? Well, it depends on alpha, first of all. You cannot say 2 or anything unless you know what the alpha here is. If alpha is 1 over 2, then it is 2, by the way. But that alpha is any number. That eventual value that you will have here is 1 plus alpha squared plus alpha cubed plus alpha to the 4, etc. So it's a power series sum. It's this sum, summation k from 0 to infinity, alpha to the power k. Do you remember what this was? If this top value is n, then you should have 1 minus alpha to the n over 1 minus alpha. That's from calculus. And we know that n goes to infinity and alpha to the n goes to 0. Because alpha is less than 1, so its infinite power will shrink down to 0. And it is 1 over 1 minus alpha, which is this limit value. So here you have 1 over 1 minus alpha. If alpha is 1 over 2, it precisely makes it 2 then. But what are the others? For example, what is this value? Which is y of 3. Y of 3 is 1 plus alpha square plus alpha cube, isn't it? This value is 1 alpha square alpha cube. Here y4 is 1 alpha square alpha cube alpha to the 4. So in general, y of n is summation k from 0 up to n. Okay, convince yourselves about this formula. Alpha to the power k. And when you write it like this and put it inside a box, I'll give you 10 points, full credit. Well, I will give you 9 points out of 10. I'll tell you why it's not a 10 points, but it's almost correct. Y of n is equal to this one. Starting from n is equal to 0 and onwards. For example, if n is equal to 0, there will be only one term, which is alpha to the 0, which is 1. Isn't y of 0 1 anyway? It works exactly that way. So we generalize the output to become like this. It would be wise if you say that the output is this times u of n, because the formulation is not valid for negative n's. It starts from 0 and onwards, and you can force it by multiplying this expression by u of n. Now this one makes 10 points. Without this u of n, almost 10 points. Okay? So this is one way to solve the output or find the output. After the break of 15 minutes, I'll give you an alternative formula for evaluating the same convolution sum, and usually students prefer that. Okay?